So today we're going to take a look at Exam 9 material, Chapter 18, on redox reactions in electrochemistry. And as usual, I've got some review document problems selected and highlighted here. So we're going to work at them. Let's see, turn this on. Yeah. See how many of these can I get on here at once? Oh, don't do that many. Let's do it this way. That should work. Okay. Number one. Consider the following reaction. Barium plus chlorine, which we know is diatomic, yields barium chloride. First of all, is that right? Chlorine is a halogen, so it's going to come in at a -1. Barium is an alkaline earth, which is a +2. So one of these and two of those makes one of those. That looks good. Which of the following statements is true? The barium atom is losing electrons, therefore it is oxidized. Okay, so we're going to look at the electron flow. So before we look at the answers, the rest of the answers, we probably should take a look at where the electrons are going. So remember that this one is 0 oxidation state. 0 oxidation state. And we just gave the oxidation states from their position in the periodic table. This one's an alkaline earth, so it's a 2+. This is halogen, so it's a 1-. So what's happening to the barium? Barium has lost electrons because it went from a 0 to a 2+. It lost 2 electrons per barium times 1 equals 2 electrons. Okay. I'm going to have to do a little, I need to leave myself room up here. So this one, right? Chlorine has to gain electrons. It gained 1 electron per chlorine atom times 2, right? 2 equals 2 electrons. Okay, so what has happened to barium? Oil rig. Oxidation is loss. So loss is oxidized. And gain is reduced. Okay. Now we can look at our answers and see which one's right. Barium atom is losing electrons. That's true. Therefore, it is oxidized. That's also true. So I think we found our answer. Because there are no oddballs down here, like 2 of the above, none of the above, that type of thing. Right, the rest of them should be false. Chlorine gain electrons, oxidized, wrong. Barium gain electrons, wrong. Chlorine lose electrons, wrong. Okay, so we do have our answer, A. Let me see here. What if this is working better? Yeah. It's a little better. Okay. Number 2. In the reaction 2, calcium plus oxygen yields what? 2 calcium oxide. Okay. The calcium is what? We're asked, we need to know where the electrons are going. But in this case, we only need to know in reference to calcium because that's the question. So what's happening to calcium? Oxidation state 0, 0. Calcium is an alkaline earth. So in compound, it's going to be 2 plus, and oxygen is 2 minus from our rules. So this calcium went from here to here, and it had to lose electrons. 2 electrons are calcium. Okay, so if it lost electrons, that means it was oxidized. And there's your answer. Calcium is oxidized. Let's see if I can page. Yep, number 3. In the reaction, strontium, which is a metal, and fluorine, which is a gas, yield SRF2, which is a solid. The fluorine is what? Okay, in this case, that's a 0. Fluorine is a -1. Okay. So when we went from here to here, fluorine had to gain 1 electron per fluorine atom. And that's all we need to know to answer the question. The fluorine is reduced, right? Rig, reduction is gain. So that means, well, the answer is A. Fluorine is reduced. Number 4. We're taking these first ones in order. Then when we get when we hit some repetition, we'll skip those. Oxidation state of sulfur in K2SO3. By the way, what would we name that compound? Right? Type 1, type 2, type 3. Metal, polyatomic ion. A metal with only 1 possible charge, type 1. So this would be potassium. Then we have to know, what is SO3? SO3 is a polyatomic called sulfite. So that's the name. Now, how about the oxidation state of sulfur? Well, we don't have any rules for sulfur. We do have rules for the potassium as an alkaline metal. It's a +1. And oxygens are 2 minus. So the potassiums together are 2 plus, and the oxygens together are 6 minuses. This is a neutral compound. So these two together are -4. That means that 1 sulfur has to balance that -4 with a +4. And we're A again. How about number 5? Oxidation state of chlorine in lithium chloride. Well, lithium is an alkaline metal, so it has to be a +1. In this case, we don't have to make any assumptions about chlorine. We can deduce chlorine. This is a given rule, +1 always. So chlorine has to be a -1. There it is right there. Okay, what's next? 6. The oxidation state of carbon in CO2. Carbon dioxide. In this case, we don't have a metal nonmetal, we have 2 nonmetals. So we got to fall back on the rules. Oxygen is -2 oxidation state, even though it's not charged, right? Because this is a covalent compound, right? 2 nonmetals. But its oxidation state for bookkeeping purposes is 2-. That means the total for oxygen is -4. That means that one carbon has to balance that -4 with a +4. Okay, so there it is right there. Number 7. It's like we're going to get into polyatomic land here. What's the oxidation state of sulfur for SO4, 2-, which is the sulfate polyatomic ion? The rule says that all the oxidation states for every atom in there added together has to equal that charge. So if oxygen starts off at a -2, then we have -8 total for oxygen. But we got to hold out 2 minuses for the charge. Right? So we really only need to balance the -6 with that sulfur. So the sulfur is going to be a +6. All right. How about, oh, we skipped that. Well, we can do it while we're here. It's not marked. This is the manganate. I think that's right. Manganate is -1. I'm going to check that just to be sure. I think it's right. You never know. Let's see, Mn. Yep. No. That's the permanganate. MnO4 with 1- is permanganate. Yeah, I wonder, is that the right permanganate? Yep, that's what it says. Okay, so for the permanganate, we have to end up with a -1 charge. So -2 to start with means -8 total, and -7 is all we have to balance. So this is a +7. There it is right there. Okay, we slid that one in. It's kind of good we did, because MnO4 can either be a -1 charge or a -2 charge. And it's important to know the difference. Let's see. Number 9. Let's see, H2CO3. Okay. Let's assume that's in aqueous solution. So what would that be? It's got to be an acid because it's preceded by the hydrogens. So if this is an aqueous solution, and that's the carbonate ion, polyatomic ion, it's got oxygen in it, so we don't say hydro. So H become X. This would be carbonic acid. That's the same stuff that you'll find in pop. Dissolved carbon dioxide makes carbonic acid. Okay, now let's get to the problem. Oxidation state of carbon. Right? We know that hydrogens by rule are +1s, oxygens are -2s. So this is a +2 for the hydrogens, -6 for the oxygens. That means we have a -4 that has to be balanced by carbon. So carbon's a +4 because that's a neutral compound. We didn't have to hold out any charges. And that makes the answer 4. Here we go. Number 11. Let's see. Be careful of the wording in number 11. The oxidation state of rubinium. If it stopped there, what would the oxidation state be? 0. Oxidation state of rubinium. But this says rubinium in any compound. So that means you have to say what group is it in and what's its likely charge. Rubinium is an alkaline metal, which means in a compound, it's going to be a +1 charge. So its oxidation state will be +1 in a compound. All right. 11, I got one peeking down here. I think I better go down and scroll this one. Too far. There we go. Number 12. The oxidation state of oxygen. Now this one is a bona fide diatomic element, which means the oxidation state is 0. Okay. Doesn't say that's in a compound, it just says there's your element, what's its oxidation state. Under standard temperature and pressure conditions, it will be O2, and each oxygen will be oxidation state 0. Okay. That's page 15. All right. What's the oxidation state of phosphorus in this compound? Mg3PO4 twice. Right? So what is that? Well, it's a type 1 compound, magnesium phosphate. That's it. That's the name. Is it written correctly? Phosphate is a polyatomic ion with a 3- charge, right? So 2 times 3- is 6-. Magnesium, alkaline metal, alkaline earth, which is a 2+, which means it's a 6+. Okay? So it's written correctly. 3 of these, 2 of those, but we want to get at this one right here. You have 2 choices. You can take the entire compound and deduce phosphate from that, or you can take the phosphate polyatomic out and deal with it as a separate entity, like that. Either way will work. In this case, 4 times 2- is the -8 for oxygen, but we have to pull 3 of them out. So it's a -5 that needs to be balanced by a +5. So phosphorus is +5. If we do it this way, oxygen is still 2-. Magnesium is 2 plus, so it's a 6 plus here. We have 4 times 2 minus is 8 minus times 2 is 16 minus for oxygen. Right? So we have a minus 10 that has to be balanced by phosphorus. But there are 2 of them. 2 phosphorus means that each one has to be a plus 5. And we get the same answer. But I think it's easier to pull that polyatomic out and deduce it from that. Either way works. 17. Let's see, before I forget, let's see, Michaela. All right. 17. What's the oxidation state of chromium in dichromate ion? Okay. So here we go again. Oxygen is by rule. -2 times 7 is -14. But we hold 2 negatives out for the charge. That means -12 is all we have to balance with these 2 chromiums, which means they both have to be +12 together. That means each one is a +6. Right here. Okay. Looks like we got some repetition, so we're going to skip a few. And 28. In reacting, metal atoms characteristically do what? Become anions, lose electrons, decrease in oxidation state, form covalent bonds. 2 of the above. Well, let's see. Since we got 2 of the above, we're going to have to check them all. Okay, so the first one, do metals become anions? What's an anion? An anion would be like a metal with a negative charge. That typically does not happen. In a chemical reaction, metals become positive ions. So A is wrong. B, they lose electrons. That is true. This one is correct. Metals typically lose electrons. How about C? Decrease in oxidation state. So if we go from here, 0, to there, is that a decrease or an increase? That's an increase. So C is wrong. They don't decrease, they increase oxidation state. They form covalent bonds. Non-metals together form covalent bonds. Metals with metals form a bond that we haven't studied. It's called the metallic bond. So that's just general information. You don't have to remember that. But metals do not form covalent bonds. Okay? Only one of them is true. That means E is false also. All right, 29. Which statement is true of the following reaction? Well, let's see what kind of reaction. 2 potassium, copper 2 chloride yields. I didn't leave myself very much room, did I? Potassium chloride plus copper. Okay. So what's happening in this reaction? Looks like we're interested in oxidation reduction, so we need to deduce what's going on here. Well, first of all, is this a redox reaction? Our rule of thumb says that's an element here It's in a compound there. That's a redox. So that's 0. This one is 0. Chlorine we have to assume is a -1 as a halogen. So that means this one's a +2. Chlorine again, -1 and +1 here. Okay, so what's happening? Well, potassium is going from 0 to +1. It's lost 1 electron per potassium. Chlorine is going from a -1 to -1. It hasn't changed. Copper is going from +2 to 0. So copper has gained 2 electrons per copper. Now, to answer the question, we don't have to balance this, say how many electrons. We just need to know, are they gained or lost? In this case, if we look at A, copper is reduced. Copper gains electrons, it is reduced. That is true. So the others must be false because we don't have any oddballs in there. Chlorine is reduced. No, chlorine doesn't change. Potassium is reduced. No, potassium is oxidized. Copper is oxidized. No, it can't be reduced and oxidized both. So D is also false. Chlorine is oxidized. No, chlorine doesn't change. So our answer is A. Copper is reduced. All righty. I see it peeking down there. Let me scroll it a little bit so we can get it positioned properly. See, we got any more down there? Oh. Okay. There. Number 30. In which of the following does nitrogen have an oxidation state of +4? Okay. So we're going to have to do each one until we find the right one. A, B, C, D, and E. So the first one is HNO3, nitric acid, nitrogen dioxide, dinitrogen monoxide, ammonium chloride, and sodium nitrite. Okay, so we're looking for +4. +4 in there somewhere. All right, this is going to be 2 minuses times 3 is -6. +1. So that nitrogen has to be a +5 to balance. +1, +5, -6. So A is not in. This one has 2 times -2 is -4. There you go. That nitrogen is a +4. Actually, if you're in a hurry, like on a test, we can stop here. That's it, we're done. But suppose I give you a question like this and I say, I give you a different number, not +4. So we better do the rest of it just in case. -2 for this one, which means those two have to be +2. So each one is +1. This would be, actually, we don't care what chlorine is because we know ammonium is NH4+. So these 4 pluses, we have to hold one out, +3, -3 for that nitrogen. How about this one? Nitrite is a -1. So this is 2 times -2 is -4, but we hold one out for -3. That nitrogen is a +3. So nitrogen, in this case, we've got a +3, a -3, a +1, a +4. and a +5. Nitrogen's all over the place. And if you look in your periodic table, in the upper right-hand corner of the one I gave you, you'll see a list of values, pluses and minus values for each element. In nitrogen, you'll find a lot of them. And that's why you have so many of those numbers in there, not because they're charges, but because they're oxidation states. Usually, let me check this before I say it. Look at the periodic table. And if I can find it, here we go. Yeah. Usually, in those squares where you have the elements and you see the list of numbers, the one at the top can either be an oxidation state, or if that element is in an ionic compound, it will be the charge on the ion. So the first one at the top is potentially the charge. But all of them together can be any oxidation state as deduced from your calculations. All right. 30, let's see, I need to scroll a little bit here. I think I've got an E hiding down here. Yep, here it is. 34. Which species is reducing agent? So let's see, we've got a titanium chloride. Actually, titanium 4. If this is a -1, that one has to be a +4. So this is a type 2 compound. Titanium, Roman numeral 4, chloride. And that is a liquid. And then oxygen gas yields titanium 4 oxide. Let's see, that's a solid. And I ran out of room. 2 chlorine gas. Okay, so what species is the reducing agent? Let's see, what's happening to these things in here? Chlorine's -1. This is a +4. That's a 0. -2. That makes this a +4. In this case, nothing happened to titanium. It did not gain or lose electrons. Oxygen went from a 0 to -2. So we can go ahead and do this one. Right? Gain 2 electrons per oxygen. And the chlorines went from a -1 to a 0. So chlorine has lost 1 electron per chlorine. Okay, so if chlorine is, let's see, which species is the reducing agent? The reducing agent is the one that's oxidized. It causes the reduction of some other element by oxidizing itself. It gives up electrons to go to reduce something else. So the reducing agent has to be oxidized. Loss of electrons means this is the reducing agent. Agent. Right? In this case, the best answer is titanium 4 chloride is the reducing agent. Okay. 38. In the reaction, phosphorus plus chlorine gas yields 4 PCl5, phosphorus pentachloride. What are we looking for? Phosphorus is what? What happens to phosphorus? It's 0 here, chlorine is 0 there. This phosphorus is what? Okay, we're going to have to assume that chlorine, in this case, is -1 oxidation step. Otherwise, we're stuck. So that means this phosphorus has to balance those 5, so it's a +5. So we're going from here to here, and we had to lose a loss of 5 electrons per phosphorus. Right? So oxidation is loss. So phosphorus is oxidized. Okay. Oh, it looks like the next one's based on the same reaction. What happens to the chlorine? Chlorine went from 0 to -1. So we gain 1 electron per chlorine. Chlorine then is reduced. Okay, and that would be right here. Chlorine is reduced. All right, let's see. There's another one. 44. In the reaction, magnesium plus sulfuric acid yields magnesium sulfate plus hydrogen gas. Which element, if any, is oxidized? Well, is this an oxidation reduction? There's an element, it's in a compound. Yes. So if it's a redox reaction, something has to be oxidized. And so let's do some bookkeeping here. 0 and 0 for those elements. Right? What about that sulfate? Did it change? No. Sulfate didn't change. So the sulfur was neither reduced or oxidized. It's the same as it was on both sides. So we can ignore that. This hydrogen, though, since this is a 2-, oh well, by any rule, hydrogen is +1. Right? So +1 to 0, we can do that one right now. Means that hydrogen had to gain 1 electron per hydrogen. So magnesium is going from a 0 to what? This has to be a +2. It is an alkaline earth. By definition, a +2 charge. Right, so we had to lose 2 electrons per magnesium. That's how you go from a 0 to a +2. You lose 2 negatives. Okay, so the question is, which element is oxidized? Oil, oxidation is loss. Magnesium is oxidized. Okay? Let's scroll to the next one. Oh, it's better Get down here and scroll that one up. Get both of them. There we go. 48. All right. In the following reaction, which species is the reducing agent? Okay. It's kind of faint, but I can read the charges, and I'll put them up here on the board. We've got 3 copper, that's element, plus 6 hydrogen protons, plus 2 HNO3, and then we have, I'm going to have to drop it down. 3 copper, 2 plus 2 NO, no charge, and 4 waters. 4 water. Okay, which species is the reducing agent? So remember, the reducing agent is the one that is oxidized. It causes the reduction of something else. So it itself has to be oxidized. So we're looking for the one that's oxidized. There's oxidation state. This water is 2 minus here, plus 1 there. There's a plus. This is a plus 1. This is a minus 2. And this is a 0. I think we can save ourselves a lot of trouble. Which one is oxidized? Copper goes from 0 to 2 plus. Right? It has a loss of 2 electrons per copper. It is oxidized, which makes it the reducing agent. Right? We can figure out which one is reduced. Hydrogen is not reduced, the oxygen is not reduced. So I would focus on the nitrogen. If the question were, which one is the oxidizing agent, then which one is reduced? So this is minus 2, that means this has to be a plus 2. This one is minus 6 here, plus 1 there. So this one is a plus 5 for that nitrogen. It goes from a plus 5 to a plus 2. It has been reduced. So nitrogen then, or this whole species, would be considered the oxidizing agent. Okay. (49) Answer the following questions that refer to the unbalanced reaction shown below. The unbalanced reaction. Determine the coefficient for the iodide ion. This one right here. Let me see. I got a sneaking suspicion that there's more to it. I ought to keep this one on the board until we get all of them answered. 49. Well, there are some, but I didn't pick them out. We're going to balance the whole equation anyway. All right. So what are we going to do with this one? Can we use the quick abbreviated form? Nope. There's an oxygen here. As a reactant, that oxygen is in the reactant side. There's no oxygen over here. So we're going to have to split it and do half reaction method. What we need is to find out, well, we're going to have 2 equations. This chromium is going to that chromium, and this iodide is going to that iodide. Right, so we know those are, just haven't decided which one's which yet. So let's see, we're going to have, let's put it up here. Cr2O7, 2 minus, that's going to go to Cr3 plus. Okay, and then this one is going to go to 7. All right. So the simplest way to answer this one is to look at that one. This one goes from minus to a 0. Iodide is oxidized. That's the oxidation step. This one must be the reduction step. So now we can calculate, we already know what these oxidation numbers are. We need this one right here. So 7 times 2 minus is minus 14. 2 minus for that oxygen. And then we have to hold out 2 minuses. So plus 12 over here, that means this is a plus 6. All right, so now we know. Next, what do? We balance the non-oxygen, non-hydrogen elements first. We've got 2 chromiums, we need 2 chromiums. We've got iodine, 2 iodines there, we need 2 iodines. Now we can do the balance the oxygens first. We have 7 oxygens on this side. We balance the oxygens with water. Okay. That means on this side, we need hydrogens. 14 hydrogens. Okay. How about this one? There are no oxygens down here, so we're done with that one. Now we can balance the electrons. Okay. This one, we're going from 1 electron per iodide to 0 electrons. So we lost an electron for each one, but there are 2 of them. Okay, oxidation puts the electrons on the product side. Reduction puts the electrons on the reactant side. So in this case, we're going from a plus 6 to a plus 3, which means we had to gain 3 electrons. But there are 2 of them. There are 2 chromiums. So we actually gain 6 electrons. All right. Now what do? Before we can put these back together, we have to reconcile the electron numbers. If we multiply this equation by 3, we will get 6 electrons. Okay. So that makes this a 6, this is a 3, and that's a 6. Okay. All right, so now we have 1 dichromate ion. Let's see how far over can I move. 1 dichromate. Let's keep in the same order. Next, iodine, 6 iodide ions. And then we got rid of the electrons, they balance. Now on this side we have 14 hydrogens. On the other side, let's go to the chromium ions. Okay. And then we have the iodines. And then we have 7 waters. Okay, is that everybody? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, can we reduce it any further? That's a coefficient of 1. No, we can't reduce it any further. So now we can answer our question. Right? What's the coefficient for the iodide ion? Iodide ion is 6. That's it. Okay. We go to the next page. What's the coefficient for the chromate, the chromium 3 ion? 2. There you go, right there. Determine the coefficient for water in the balanced equation. Right? There's no water in this part of it, but once you balance it, there is water. And there's a 7. Okay, I didn't scroll far enough. So let's scroll down and catch, it's probably E there. Oops, too far. There it is. Oops. 7. Okay. So we actually answered 3 problems out of 1 calculation. All right, 52. In the reaction of sodium bromide with chlorine gas, sodium bromide with chlorine gas, diatomic, to form sodium chloride plus bromine gas. The appropriate half reactions. Okay. I assume here that the half reactions must be balanced. Fortunately, there are no oxygens here, so we don't have to introduce water or hydrogen ions. What we do need to do is separate out the oxidation and reduction steps. That's a 0 oxidation state, that's a 0. There's the -1, +1, there's a +1, there's a -1. So, what's going on here? Sodium doesn't change. Chlorine goes from a 0 to a -1. It is reduced. Let's see. They want oxidation first. So let's do the oxidation. Okay. So bromine is oxidized. It goes from a -1 to a 0. It lost an electron. So bromine -1, that's an ionic compound, so we can do that. Goes to bromine there. Reduction then is the chlorine goes to chloride. Okay. Now we need 2 of these. Okay. And we need 2 of these. How about electrons? Well, -1 to 0 is 1 electron gained per bromine, but there are 2 of them. Chlorine lost electrons. Excuse me. My mistake. There we go. Oxidized. Chlorine gained an electron per chlorine, but there are 2 chlorines, so it had to gain 2. So there you have your half reactions. 2 bromine, 2 bromides. It looks like this one. That's the only one with 2 bromides in the oxidation step. And let's see, on this side, chlorine plus 2 electrons yields 2 chlorides. That's right. B is the answer. Okay. We're doing on time. We're doing pretty good. 56. When the following reaction is balanced in acidic solution, what's the coefficient of water? Well, let's look at it and say, all right, is there going to be water here? There's oxygen there. Yeah, we're going to have water in this one. And in acidic solution. So we're probably going to add water and hydrogen ions. So let's split it up. What's happening? Zinc is going from 0 to +2. It is oxidized. So the oxidation step should take us from zinc to zinc ion. The reduction step then should be the nitrate ion to the ammonium ion. All right. So we got one zinc, one nitrogen, but we don't know. Let's go ahead and figure out what their oxidation states are. That one's 0. This one is +4 for all those hydrogens. We've got to hold one out. So that means this one is -3. That's a -6 for the oxygens, -5 because we hold one out. That means this one is a +5. So this one, nitrogen was reduced all the way from +5 to -3, which is how many electrons? 8. 8 electrons were gained. We'll put those in a minute. One zinc, that's good. One nitrogen, that's good. Oxygen, we have 3 oxygens. So we need 3 water. So now we have 6 hydrogens on this side to balance those 6. Now we can do electrons. This one was oxidized, so we're going to have 2 electrons over here. 2 electrons lost to get to that 2+. What do we say here? 8 electrons were gained for 1 nitrogen. That's all we have. Now we just need to reconcile. This one needs to be multiplied by 4 to give us 8 electrons over there. So that's going to be 8 here, 4 there, and 4 there. Okay, let's go back to the question just so I don't get too far afield. What's the coefficient of water? Right. Can we add these together now? Yeah. Electrons are balanced. So what's the coefficient of water? 3. We don't have to go to the trouble of bringing them all down. We've got our answer right there. 3. All right. So let's go to 58. I'm going to leave that one up there just in case. You never know when a subsequent question might need that equation. Let's see. No, doesn't need it. So we'll erase this one then. That was 56, now 58. I might start to get weak on me. '58. Which of the following is true for a galvanic cell based on the following reaction? Okay, remember a galvanic cell. You have 1/2 cell is the reduction side and 1/2 cell is the oxidation side. They're connected by a wire and a salt bridge to complete the circuit. So what's the question? Which one's reduced? Which one's the anode? Okay, so we need to describe this reaction completely. We're starting off with zinc plus copper 2+, and then we get zinc 2+ and copper. Okay, so which one's which? Well, zinc yields this one. It had to lose 2 electrons. Okay, and the copper yields this one. It had to gain 2 electrons. All right. So remember what our definition was. Well, first of all, zinc is oxidized. And copper 2 plus is reduced. Then we need to name the half cells. Which one's the anode, which one's the cathode? Cathode is always the one where reduction takes place. So reduction, this would be the cathode. This one would be the anode. All right, now we can probably answer it from there. Zinc is being reduced. No, zinc is oxidized. The zinc serves as an, or did I get those backwards? Zinc serves as, oh no, that's right. Zinc is the anode. So B is correct. B is a correct answer. Copper 2 plus is being reduced. Yes. So C is a correct answer. Copper serves as the anode? No, it's the cathode. So you've got 2 correct answers here. That's why E is the answer. Both of those, B and C, are correct. All right. Well, let's see if I can scroll a little bit. Maybe get both of them on there at the same time. Yep. 60. In a car battery, which of the following is the electrolyte? What's the electrolyte? The electrolyte is the solution in any half cell. The electrolyte is going to have dissolved ions in it. So for the lead acid battery, your car battery, the electrolyte is the same for both cells because both cells are in the same solution. And that solution is sulfuric acid, H2SO4. Right here. Okay? And I put a little note in here for myself. What about cell phone batteries? What is the cell phone battery called? It's called lithium ion. Now, we didn't put that reaction up here. And it's a little beyond this class to work on that one because the chemistry of the lithium ion battery in your cell phone is relatively complex. And it has the nasty habit of easily overcharging. Recharge a lithium ion battery and you go past its the point where you have balanced anode cathode and you start to force it further, then you end up with fires and explosions. So all lithium ion batteries have built into them circuitry that senses when the battery has reached full charge and will not allow any further push from external voltage to drive it too far. Built-in electronics that keep it from doing that. But the cell phone battery is called lithium ion. Now, why lithium? Well, there's a thing called energy density. And when we're talking about batteries, the holy grail of batteries is a battery with very large energy density. That is, for a given weight of battery, you can get a certain amount of energy out of it. And this is measured in joules. And since lithium is the third element in the periodic table, it's very light, takes up less room, very small amount of room. You can pack a lot more lithium ions together than you can for lead. And with the sulfate and lead oxide, they take a lot of room and they weigh a lot. So the energy density for a car battery is very low. But a lithium ion battery needs to be light and have lots of energy in it. That's why they use them in cell phones and computers. Okay, that's enough of that. How about 61? I'm starting to get a light on me too. In the lead storage battery, lead oxide is found at the cathode, anode, so forth and so on. All right, we got to look at what's the chemistry behind the reaction. So if we look at just one cell in a lead acid battery, then we're going to have the lead plate here, and we're going to have the lead oxide here. So this one has a 0 oxidation state. This one has a, let's see, there's 2. This is +4. Okay. Down here, you have sulfuric acid. So this one is going to oxidize and become lead sulfate with a 2+ charge. So for this one, that lead atom has lost 2 electrons. Where are they going? They're going through the external circuit. 2 electrons are going this way. So when they come over here, this lead is going to be reduced, and it also will produce lead 2 sulfate. Okay. So now we can say which one's the anode, which one's the cathode. The cathode is the half cell for the site of reduction. Here's reduction taking place. That's the cathode. This is the anode, where oxidation takes place. So now let's see if we can answer the question. In a lead storage battery, PbO2 is found at the cathode. That's where reduction takes place. So on the outside of your battery, it has positive and negative terminals. This one is the negative terminal. That's the electrons coming out. This one's the positive terminal. Electrons going in. Okay, that was 61. Let's see what else we got. 63. I'll just draw it bigger. It's getting kind of faint, so I'll make the letters, the numbers bigger. When the metal corrodes, what is happening chemically? Metal corrosion. What's happening? Well, what are you starting off with? Well, you're starting off with a metal. And what's the metal doing? Well, it's either converting to metal oxide or usually a metal sulfide. Those are the 2 common forms. But what it's doing is it's being oxidized. It's losing electrons. So we get electrons over here, because this is now a positive charge, right? So the metal is being oxidized. It is losing electrons. The metal loses electrons. The metal doesn't gain electrons. Electrons are not involved? Oh yeah, they are. Metal is combining with nitrogen gas? No. None of these, well, we do have one of them. That one right there is true. Metal atom loses electrons. What it's trying to do is get back to its one of its possible compounds that we found in the ore originally. When the metal was purified from its ore, it was combined. So in that case, smelting of metals is a reduction process. We add electrons to the metal and separate it from the compound. Now we have the pure metal that was positive charge before in the ore. Now it's a metal that's been reduced to its metallic form, zero state. That's 63. Let's see. 66. Balance the following redox equation in acidic solution. What's the coefficient of water? Okay. Let me be sure we got enough time to do this. 66. Yeah, I think we do. So what is CH3OH? That's methanol, wood alcohol, the kind that will make you go blind if you drink it. Oh, you'll get drunk, but you'll also go blind. All right. So let's split this reaction up into its oxidation and reduction steps. So what are we looking at here? Chromium, we know from our previous example, is a 6+. And this chromium ion here is a 3+. So we go from a 6+ to a 3+. The chromium has been reduced. So we can write our reduction step here. It's going from this one, Cr2O7 minus with a 6+ charge. Actually, it is charged, but it has an oxidation state of 6+. And it's going to this one. That means the oxidation step must be the other one, CH3OH. Goes to CH2O. What is that? I'll tell you. That's formaldehyde. Everybody knows formaldehyde. If you've had a biology course or anatomy and physiology course where you dissected a preserved specimen, you probably smelled formaldehyde. Okay, so this one's the oxidation. All right, let's go ahead and do the oxidation states. Which one's doing what? That was +1, this one's -2, -2, +1, +1. So the oxidation is occurring on the carbon. What is the number for carbon here? Well, let's see. We've got a +1, and actually 4 times +1 is +4. And we have a -2 for that oxygen. That means this carbon has to balance a +2 with a -2 for that carbon. How about this side? -2 and a +2. Well, +1 times 2 is +2, and -2, that's 0. So this one is 0. That carbon is 0, oxidation state. Okay, now we can balance the elements. 2 chromiums. Go. This one has a carbon here and a carbon there. Right? We don't balance the oxygens or hydrogens yet. So the carbons are good. Let's move some of the clutter. About that. We just need to know what the carbons are doing. Okay, so now we can balance the oxygens. So on this side, we need 7 oxygens and 14 hydrogens on this side. Okay. Down here, we have 1 oxygen there, 1 oxygen there. But we have 4 hydrogens here and 2 hydrogens there. In this case, we don't have to balance the oxygens. we only need to balance the hydrogens. So if we got 4 hydrogens here and 2 there, that one means we need, we need 2 more hydrogens. So now we have 4 hydrogens here, 2 plus 2 is 4 there. 1 oxygen, 1 carbon, 2 chromiums, 7 oxygens, 14 hydrogens. Okay? So now we need to do the electrons. What are the electrons doing? Well, we've gone from 6 plus for this chromium to a 3 plus, means we had to add electrons. How many electrons? Well, 3 electrons for each chromium, but there are 2 of them. So that means 6 electrons. Okay? On this side, we're going to oxidize. So we're going from -2 to a 0, which means we're going to have an extra 2 electrons over here. All right, oxidize, put the electrons on the product side. Okay, so now we need to reconcile. We got 6 electrons, 2 here. If we multiply this whole thing by 3, right, then we got a 3 here, 3 there, 6 there, and we get a 6 here. Now, how about the question? Well, let's see. The question is, what's the coefficient of water? Coefficient of water is 7. Right? If we add them together, that's what we get. And there are no other waters on this side. So that's all the waters there are, just 7. Looks like the next one is also using that same equation. So let's scroll down and catch this one too. Yeah. Let's see. What's the coefficient of hydrogen ions? Okay. Hydrogen ions. Notice we have 14 hydrogens here and 6 hydrogens there. Right? So these are going to cancel and leave how many here? 8. So the coefficient on hydrogen ions is 8. Okay. Let's see here. 70, let me scroll this a little bit. Well, that one only goes down to D. All right. 70. How many electrons are transferred during this reaction when balanced? Notice that there's no oxygen here. There's no hydrogen, there's no oxygen. So we can balance that. We don't have to split this one up. All we have to do is assess the oxidation states and where the electrons are moving and say how many electrons total are being moved from one place to the other. So let's say gold. That looks like a complex ion. Yep, because the charge is outside. It's assigned to the whole thing. And this is a metal with non-metal. That's a complex ion. And we have copper. And we're going to make it's an equilibrium with gold plus chloride ions plus copper 2 plus. Okay, this copper is 0, that gold is 0. Chloride doesn't change. So we don't have to worry about the chlorine. There's nothing happening to the chlorine. The gold, though, if this is for bookkeeping purposes, if this is -1, that's -4 total. Hold minus out, -3. This is a +3. So gold is going from +3 to 0. So gold is going here, here, here. That means it lost 3 electrons per gold. Copper is going from here to here. Copper gained 2 electrons per copper. Okay, notice that this is an even and this is an odd. So how do we reconcile an even odd? We cross multiply. So how do we get, what's the common denominator in mathematical terms? 6. The common denominator. If we multiply this one times 3, and this one times 2, then we'll get 6 electrons. Okay? So we would just need to say, all right, for the gold, we need to multiply by 2. So it'll be 2 of these and 2 of those, and 3 coppers, 3 coppers, 3 coppers. But to answer the question, all we need to know is how many electrons are transferred. 6 electrons are transferred. Right? Answer the question, move on. Oh, we got another one coming up. How many electrons are transferred in the next one? 71. So we've got 10 metal, 2 hydrochloric acid, 10 to chloride, 2 plus, and hydrogen gas, 0. Right, this is -1, this is +1. Okay, how many electrons are transferred? Oh, that's why this one doesn't have an E. Somehow this one got, there should be an E down here with this answer. It got chopped off there somehow. So E is not enough information, and D is 4. Let's find out how many electrons were transferred. Is this balanced? It looks to me like it's balanced to begin with, right? 110, 2 hydrogens, 2 chlorines. We're balanced. So all we have to do is count up how many are moving. If we go from this one to this one, that's a loss of 2 electrons per 10. Hydrogen, well, let's see, times 1 equals 2 electrons. How about this one? Hydrogen's going from +1 to 0. So it's gaining 1 electron per hydrogen times 2 equals 2. So how many electrons are transferred? 2. Okay. That's 71. Let's see here. Oops. Oops. There we go. 75. Give this one a rest. In an acid dry cell battery for which the reaction is, and it looks to me like it's balanced. Zinc, 2 nitrogens, 8 hydrogens. There's 2. 6 is 8, yep. 2 chlorines, 2 chlorines, 2 manganese, 4 oxygens, 3 plus 1 is 4. That one is balanced. What is oxidized? Okay, so let's write this one out. Zinc plus 2 ammonium chloride plus 2 manganese 4 oxide. Then we have zinc chloride, and we have 2 ammonias, and we run out of room. So we have What is that? What's the oxidation state for manganese? Well, if this is -2, this is -6, +6. This one's +3. And water. Okay. So let's identify all the players. Zinc is 0. -2, -2, +1. +1 means this one's a -3. -1 +2. -2 +4. -1 +1. So in this case, we've got a -1 and a +4, which means +3. Nitrogen has to be a -3. Okay. All right. So what's the question? What is oxidized? Who's losing electrons? Let's see, zinc goes from 0 to +2. That's definitely a loss. There. 2 electrons per zinc. So that answers the question. While we're here, if that was being oxidized, who's being reduced? Let's say who's gaining, who is lowering their oxidation number? Nitrogen's not changing. Chlorine's not changing. Oxygen's not changing. Hydrogen's not changing. Manganese. Manganese is gaining 1 electron per manganese. But there are 2 of them. So we're balanced. Just as a point of information. Okay. Oh, there it is again. Which one is reduced? We got that already. Manganese is being reduced. And do we have another one based on that same? Don't see it. Oh, here we go. There's another one. What's acting as the oxidizing agent, the one that's reduced? MnO2. Here. That's the oxidizing agent because it's being reduced. Let's see. Let me look, see if there's any more. Based on that same equation, I don't want to erase it if we're going to use it again. One. No. Okay, I can erase it. Okay. Let's see. This one in basic solution, 85. So we have silver plus copper yields silver metal plus copper ion. This reaction in basic solution. Okay. There's no oxygen, there's no hydrogen there. It doesn't matter. That's a basic solution. It makes no difference to balancing this equation. So all we have to do is balance it. So if this one's 0 and it's going from here to here is a loss, 2 electrons per copper. This one is a gain, 1 electron per silver. we need 2 electrons, right? So we have to multiply by 2. There we go. That's balanced. The equation is balanced. The sum of the coefficients is 2, 3, 4, 5, 6. Okay? Trick question. If there's no oxygens or hydrogens involved, it doesn't matter whether it's basic or acidic. Let's go down to the next highlighted one, 83. So we're going to have to scroll a little bit. Here we go. 83. Oops. When the equation for the following reaction in basic solution is balanced, what's the sum of the coefficients? Right? Okay. Do we need to split this one in 2? Yep, there's oxygen here. Well, let's see, there's 4 oxygens here, 4 oxygens there, but this one has some hydrogens. So we're going to have hydrogens over there too. Right, so we are going to have to split this one. All right, let's put MnO2. Yeah, let's put it up here first. MnO2 plus HO2 minus. And then MnO4 minus. What is that thing right there? That is a peroxide ion. It would look like this. Normally, hydrogen peroxide would be like that, right? Neutral. But if we lose one of these hydrogens, it takes a positive charge with it and leaves behind a negative. So O2H minus. So that's what this one is, in case you're interested. All right, so what's, we need to figure out which one's the oxidation step and which one's the reduction step. So we have 2 minus for oxygen, which means -4, hold down minus. Well, that can't be. Oh no. What's the rule on peroxides? Each oxygen is a -1. So these 2 together is a -2. Hold out. That's a +1. Okay, so we're good there. How about this one? Now that one's a 2 minus with a 4 minus total. That means this one's 4 plus. This one is -2 times 8 is -8, -7 because we're holding 1 out. So this one's a +7. Okay. All right. This one might be a little tricky. We know that manganese is being oxidized, so we can write that. This one, O2, that. Let's make some room here. And it ends up over here is this one. +7. That's the oxidation step. What's the reduction step? It looks to me like oxygen is going from a -1 to a -2. So this one we had to add electrons. Oops. No, we lost electrons. So this one, we had to gain electrons. That's right. HO2 minus with this -1 for that oxygen, going to what? Well, where could it go? Is it going to go to one of these? Unlikely. Probably going to water. Because that's a -2. From a -1 to a -2 means it lost electrons. Manganese. Okay. Oxygens. We got 2 here, 4 there. We need 2 more on this side. Then we need 4 hydrogens on this side. Okay. On this one, we've got a hydrogen here, 2 hydrogens there, and an oxygen there. So if we do 2 oxygens here, that means 4 hydrogens. There's 1 here already, so we need 3 hydrogens on this side. Okay? That's the trick. That's what I missed right there. Okay, now we can do the electrons. So this one is going to lose 3 electrons per manganese. Okay. Product side. This side, we gain 1 electron per oxygen. But we got 2 oxygens, right? There we go. Okay, now instead of multiplying by one of the equations by a number, we have to multiply both of them because this one's got an odd and this one's got an even. So this one has to be multiplied by 2. And this one has to be multiplied by 3. Right? That 3 here is 2 here. All right. Now we're on track. So we have 2 MnO2 plus 4 water yields 2 MnO4 minus plus 8 hydrogens. And I'm not going to do the electrons because they're going to cancel anyway. Right? This one has 3 peroxide ions plus 9 hydrogens yields 6 water. There we go. Okay. Now we have the electrons balanced. We can bring these down. So we're going to have 2 manganese oxides plus 4 water plus 3 peroxides plus 9 hydrogens. Okay. And on the other side, we have 2 permanganates and 8 hydrogens. Okay, is that everybody? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 5. Plus 2 water. Oops, excuse me. 6 water. There we go. Now everybody's down. Okay, let's get rid of the hydrogens. 9 hydroxyls here. 9 hydroxyls there. This makes 9 waters. This makes here. This makes 8 waters plus a hydroxyl. You have 1 hydroxyl left over. Okay. We've got 9 plus 4 is 13 waters. And then 8 waters on this side. So all of these waters are gone, and we have 5 left over. Okay, so now we have 2MnO2 plus 5 water plus 3 HO2 minus yields 2 MnO4 minus. Wait a minute. Hold everything. This was 14 waters on this side. And this was 4 Okay, we're looking at this one and this one. 4, 3, 9, and 2 MnO4 and 8 hydrogens and 6 waters. So we did 9 hydroxyls here, that makes 9 water. We have 9 hydroxyls here, that makes 8 waters. 1 hydroxyl, but I didn't count that one. So we got rid of these and these. Now we have 8 plus 6 is 14. 14 waters on that side. 9 and 4 is 13. So we've got 1 water on this side. Plus an H2O. That one's gone. This one's gone. It leaves us with a hydroxyl. Hydroxyl, a water, and a permanganate. Okay. On this side, we've got, I already counted for them. They're all gone. 13 on this side, 14 on that side, only 1 left on this side. Okay, all the waters are gone on this side. HO2 minus yields MnO2 plus a water plus a hydroxide. There we go. Now we add up the coefficients. 2 plus 3 is 5, 6, 7, 8, 9. The answer is 9, which is D. See how easy it is to get confused? Especially if you're trying to squeeze all that work into one little space here. You got lots of paper, you can string it out and keep track of it better instead of trying to do it all in your head. Okay, so we're done.